Okay, so we are going to start electrochemistry today. We're going to do a little bit of review of some topics from 1210, maybe a previous general chemistry course that will be useful to know, that you'll need to know for success in this chapter. So the first thing we're going to talk about are how to assign oxidation numbers. And this is a huge wall of text, but we're going to walk through this. I'm going to do some examples. So assigning oxidation states or oxidation numbers, I think with practice becomes easier. So the best thing you can do in learning how to assign oxidation numbers is practice. So a number of things here. If you have a pure element, the oxidation number is 0. If we have a monatomic ion, it's equal to its charge. The oxidation number is equal to its charge. So for instance, F minus, one atom, it's an ion, so monatomic, has a charge of -1, and so the oxidation number for F minus would be -1. I usually write oxidation numbers above the elements, especially when we're working with formulas. This is kind of a bookkeeping. The sum of oxidation numbers of a compound is 0 if that compound is neutral, or it's equal to the charge of an ion. So given this rule, we're able to basically set up an equation to solve for certain oxidation numbers if we're unsure of what they are. But there are a number of useful things to remember so you don't have too many unknown oxidation numbers. If we have an alkali metal and it's in a compound, the oxidation number is +1, so sodium, potassium, for instance. If we have an alkaline earth, it's +2, magnesium, calcium. And then here's our fluorine. Fluorine is -1 in all of the compounds. So these types of things are things you're going to want to be familiar with. The other rules that are useful, oxidation number of hydrogen is usually +1, but there are some exceptions. H2, that should be H2, where the oxidation number is 0 because this is the elemental form of hydrogen, and so the oxidation number here is 0. We also have the ionic hydrides, so sodium hydride, for instance. The rule where the sodium, being an alkali metal, has an oxidation number of +1 takes precedent, and that means that the oxidation number of hydrogen is -1. Okay. So, but usually hydrogen is +1, and then oxygen usually is -2 for its oxidation number. Those two are really useful tools to remember. There are exceptions. So O2, because that's the elemental form of oxygen, the oxidation number of oxygen in that form is 0. And then the peroxides, hydrogen peroxide being a good one to keep an eye on. This, in hydrogen peroxide, oxygen has a -1 oxidation number instead of -2. So for all of the other elements, you can use these rules plus the fact that we know that everything sums up to the charge of the ion or the molecule to solve for the oxidation numbers for others. So let's go through here and do these examples. So let's start with NO. Take a look at that one. So for NO, we're going to use the rule that oxygen has an oxidation number of -2. And so we need to solve for that of nitrogen. We can use the rule that the oxidation number of the oxygen plus the oxidation number of nitrogen is going to equal to the overall charge. This is not a great way of writing that. That's a 0. We're basically trying to show that this is essentially an equation. So oxidation number of oxygen is -2. And everything has to sum to 0, which means that the oxidation number of nitrogen must be +2. Does that make sense? All right. Work on the next one, NO2. So in NO2, again, our oxygen is going to have a -2 charge, oxidation number, but there are 2 of them. So we need to use that to figure out the oxidation number of nitrogen. And everything, again, is going to sum up to 0, which means that we're going to have -4, and we need to have +4 for nitrogen. So the subscript 2 does play a role in determining oxidation numbers for other things. Is this ringing some bells here, making sense? You guys remembering this? No. So you get yins, just yins. Questions on that one? Okay, I'll take that as a good sign. Let's do SO4 2-. What's the oxidation number on sulfur? +6. So we have oxygen, it's -2 again, times 4, plus some number for sulfur has to equal -2. So we're going to have -8. Sulfur then has to be 6 in order to get -2. All right, what about the last one? Potassium dichromate. So here in this one, we know what the oxidation number should be on potassium. It should be +1, and we have 2 of those. Chromium, it's unclear. That can have multiple oxidation states. But there are 2 of those, so we're going to need to multiply whatever that number is by 2. Oxygen -2, and there are 7 of those. And all of that has to equal 0. So now we need to solve for the oxidation number of chromium. So we're going to have, let's see, -14, -2. That's not right. All right. How's math hard right now? +2. Oh, wait, what?
The 2 in the front plus the -14.
2 in the front plus the -14,
So 2
yes.
plus 2x plus -14.
I get that, okay. Oh, duh, yeah, I'm seeing it. There it is. See, super easy to make mistakes on these. I know why y'all do that. That's not an eraser. There we go, okay.
So 2 minus 14.
Yes. Hang on. Let me erase again. Okay. 2 plus 2 times chromium plus -14 equals 0. Plus 14 minus 2 equals 12. 2 times chromium plus 6. Algebra. Questions? Next slide. Okay then. This is also from your previous electrochemistry experience when you studied redox reactions some other time. So we need to go through these terms. An oxidant or an oxidizing agent. This is something that is reduced. What does reduced mean? Something that is reduced gains electrons. E minus for electrons. The other way of thinking about an oxidizing agent is that it oxidizes something else. What does oxidize mean? It loses electrons. So the reducing agent is the reverse of that. It is oxidized. It loses electrons, and it reduces something else. There's usually some fun ways of remembering this. Oil rig is one. Oxidation is loss of electrons. Reduction is gain. What are some others people have? Leo the lion says Gur. Loss of electrons is oxidation. That's Leo. Gur. Gain of electrons is reduction. Okay. Anything else? Any other creative ones? Those are the two that I know. Truly still will go through when I'm doing these redox reactions and say oil rig in my head every time I do a problem. So keep that in mind. Unless you're doing these types of things every day, that sort of thing probably doesn't go away. Okay. So one of the things you're certainly going to have to be able to do is balance redox reactions. This is a multi-step approach. It is very easy to sort of not follow these steps and go a different route, but I highly recommend, especially if you don't know how to start at this point, if you don't have a plan already for balancing redox, that you follow these steps in this order. Okay? The way of balancing this way also means you don't have to necessarily calculate the oxidation number of every element, which saves a little bit of work. Another place of making mistakes, as you saw, just working through my algebra here. So this says balancing redox reactions in acid. That's often the way we balance difficult redox reactions. You may have done some balancing before where you didn't have to worry about whether it was in acid or in base, as we're going to see here in a couple more slides. But often our redox reactions are taking place in acid or base, and so that is why this is our approach. So this is written as 3 steps, but there's actually quite a few steps here. The first thing is to write the half reactions, and that's not necessarily a trivial thing, but essentially what it's going to come down to is writing a half reaction where, let's say you have an atom, something other than oxygen and hydrogen, show up on one side, and that same atom show up on the product side. And then we're going to look at which half reaction is oxidation and which is reduction. That step doesn't necessarily have to happen, but it is useful to see, to think about that, and I'll show you a little bit on that. The next thing we're going to do is balance each half reaction, and the way of doing that, we're going to start with balancing atoms that aren't oxygen and hydrogen. Those ones are easy to account for, so we have to make sure that everything else is balanced before we balance with oxygen and hydrogen. The way Once we have all of those other atoms balanced, the way we're going to balance oxygen is by adding water. We're usually working in aqueous solutions. And in adding water, we add extra hydrogen. And so then our last thing to do is add H plus to balance for the hydrogen. After that, we're going to look at the charges, and then we're going to add electrons to one side of the equation that we've come up with to balance charge. Once we've done all of that, that's the hard part. Then we add our equations together. We may need to multiply by a factor so that our electrons cancel, and then we can simplify things. So this steps 1 and 2 are really where it's easy to make mistakes. Once you finish all of that, the rest of it is fairly straightforward. So 1 and 2, writing the half reactions and balancing through adding the charges. Okay, so we'll do one together, and then I've got one for you all to try on your own. This question is written as a multiple choice, but basically it's asking, after we balance the redox reaction and we add H plus, or we add acid, which side does the H plus show up on, and how many are there, okay? But in order to answer that, we have to balance the whole thing. So as I mentioned before, the first thing to do is write the half reactions. If we look at our reaction, we have MnO4 minus plus Br minus yields Mn2 plus and Br2. So we're going to take the two things that have manganese, and we're going to put those on the reactant side and product side. That's going to be one of the half reactions. So we'll have MnO4 minus forming Mn2 plus. The other half reaction is going to be Br minus forming Br2 in the liquid phase. So again, just taking those elements that are not oxygen and hydrogen, separating those out so they match in the half reactions. Okay, so let's now take this equation with the manganese, and let's balance that half reaction. I'm going to leave off the phases now just for simplicity. So we balance atoms other than oxygen and hydrogen first. So in this half reaction, that's simply the Mn. So we've got manganese on both sides. We've got one on both sides, so that's balanced. So we can leave that there. The next thing we balance for is oxygen. And we add water to account for excess hydrogens on one side or the other. So we have 4 oxygen on the reactant side. To balance this, we need to have 4 oxygen on the product side. So we're going to add 4 water to balance that out. Okay. So now we need to balance for hydrogen. We just added 8 hydrogen to the product side, so we're going to need to add 8 H plus, because we're balancing an acid, there's our acid. Add 8 H plus to the reactant side. Is everyone okay up to that point? Other atoms that aren't oxygen and hydrogen, then oxygen with water, then H plus for hydrogen. The next thing we balance are the number of electrons. And the way I like to do this is to look at the charges on each of the species present on the reactant side and the product side, and add electrons so that the charges are equal on both sides of the equation. So for instance, we have 8 plus charges here from the 8H plus and 1 minus. So overall, if we add up all of these charges, we have plus 7 on the reactant side. Everyone see that? And then on the product side, we have +2. So we need to add electrons, which have a minus charge. How many and to which side will we add? I have 5. Yeah? If we add 5 electrons to the reactant side, now our overall charge is +2. So those are equal. +2 on the reactant side, +2 on the product side. We haven't had to mess with any oxidation numbers, which is great. Everyone okay with that? Okay, so let's balance, that's where we stop with this half reaction. Let's balance the other half reaction. We have Br minus going to Br2. We need to add 2, or multiply the Br minus by 2, add a stoichiometric coefficient there. And now everything's balanced. We don't need to add water, we don't need to add hydrogen, or H+. Okay? But we do need to add electrons. So overall we have a +2 charge on the reactants, -2 charge on the reactant side, and a 0 charge on the product side. And so we need to add 2 electrons to the product side in order to balance those. So we can only add minus charge, right? We only have electrons to work with. So the only way to balance those is to put them on the product side. When you're balancing redox half reactions, you should have, for one half reaction, electrons show up on the reactant side, and for the other, the product side. Maybe product side first and reactant side second, depending on how you write them, of course. But they need to show up on either side. If they both show up on the reactant side or they both show up on the product side, you probably made an error somewhere. So questions on that? Yes?
I see what we're doing, but why are we doing this? What is it doing? Adding hydrogen, adding electrons?
Yeah, so with this redox reaction we were given, it's not balanced. So you'll see, so we've got, well, you can see it mostly here without, there's no oxygen on the product side, and there's only 1 bromine on the reactant side. Because it's a redox reaction, like normally we could do that, balance the reaction, maybe we just add things and we'd be good. But because it's redox, we have to pay attention to all of these other things as well. Is that helpful? Yeah. Okay. And then we can ask the bigger why. Why do we have to do this? Yeah. Okay, so we've got down to the point now where we've balanced both half reactions for all the atoms and electrons, and so we can sum them up. But in order to do that, we have to be able to cancel out the electrons. In our overall reaction, we can't have any electrons on reactant side or product side. Okay? So we're going to need to multiply our half reactions by a factor in this case. Because we have 5 in our first half reaction, 5 electrons on the reactant side, and 2 on the product side in our second half reaction. So if we multiply this first reaction by 2 and our second reaction by 5, we'll be able to get 10 electrons on the reactant side of the first reaction and 10 on the product side of the second reaction, and then we can cancel those out. So I'm going to rewrite these half reactions. We have 10 electrons plus 16H plus 2MnO4 minus forms 2Mn2 plus 8H2O. Okay. For the bromine, we're going to have 10 Br minus, forming 5 Br2 plus 10 electrons. Now we can cancel anything that shows up on the reactant side of one reaction and then on the product side of the other. And so certainly we want to be able to cancel our electrons. And then nothing else with these two half reactions will cancel. So when we write the overall equation, we're going to have 10 Br minus plus 16H plus 2 MnO4 minus yields 2 Mn2 plus 5 Br2 plus 8 H2O. So that is our balanced half reaction, and now we can answer the multiple choice question. Questions? Yes.
Can I ask why you multiply the BR times 5 and the other?
So here, so this has a coefficient of 2, so that there are 2 bromines on both sides of the half reaction. We did that initially. And then I multiplied this whole equation by 5, so that I could get 10 electrons on this product side, which would then allow me, when I sum up the equations, to cancel with 10 electrons showing up in this first half reaction. Mm-hmm. Other questions? Yes?
Do the electrons always cancel out?
Yes, the electrons should always cancel out. So we're effectively, the other question that could conceivably be asked is how many electrons are transferred? Okay. And so that's the number that you cancel out. We're actually, in this reaction, transferring 10 electrons from one species to another. We could look at the oxidation numbers to figure out where they're going, but that's the number that's being transferred. Yes, they should cancel out. If they don't cancel out, you've done something wrong. Other questions? All right, let's do another one. Oh. Well, you guys, okay, the question was how many H plus and which side? So we have 16 H plus on the reactant side. Okay, a couple more. Let's do another one. Similar question, different reaction. Take a look at that. Have you work with your neighbor. If you have questions, raise your hand. I'll come around. We'll take maybe 5 minutes, see how we're doing. Sound good? Sounds great. Be nice. All right, I'm seeing some great work, some really good questions. So let's work through this. Okay, here we go. So let's write our half reactions. We have S2O4, excuse me, O8 2 minus, forming SO4 2 minus. That's our one half reaction. The other one is going to be NO, forming NO3 minus. So for the sulfur-containing half reaction, we can put a coefficient. We need to balance our sulfurs. We have 2 on the reactant side. We have 1 on the product side. So we can put a coefficient of 2 in front of the SO4 2 minus on the product side. And in doing so, we end up with 8 oxygen on the product side, and we have 8 on the reactant side. So those are balanced. No hydrogen to worry about, so we don't have to balance anything with H+. The only thing left to check is the charge. And so we have a 2 minus times 2 for the charge on the product, overall charge on the product side, minus 4, and then overall minus 2 on the reactant side. You don't need to do anything with those values other than just, they're used for bookkeeping, okay? They're used to make you see where charges are and how many and where can you put electrons, right? You don't need to adjust any other things. So to make our charges equal, we can only add electrons, right? We need, thank you. We need to add 2 electrons to the reactant side, and now we have a total of minus 4 on the reactant side and minus 4 on the product side. Okay with that? Okay. So for our nitrogen-containing half reaction, balance our nitrogen first. We have 1 on the reactant side, 1 on the product side, so that's great. We next add oxygen by adding water. We have 3 oxygen on the product side, and we have 1 on the reactant side. So we need to add 2 water to the reactant side to balance those oxygens. So now we have a total of 3 and 3. In adding the water, we've added hydrogen, so we need to account for that on the product side of the reaction. So we've added 4 hydrogen to the reactant side. We need to add 4 hydrogen in the form of H+ to the product side. Okay. So now we need to balance our electrons. Overall, the charge of all of the things summed together on the reactant side is 0. And on the product side, we have 4 pluses, 4 plus, and then a minus. So we have a total of +3. We can only add negative charge with the electron. So to balance that out, we need to add 3 electrons to the product side, and now it sums up to an overall charge of all of those things of 0 on the product side. So now they're equal. Does that make sense? Okay. So we've got our half reactions. We've got electrons on the reactant side, electrons on the product side, so that's good. That checks out. But they're not equal, so we can't cancel them. But if we multiply our sulfur containing half reaction by 3 and our nitrogen containing half reaction by 2, we'll end up with 6 electrons transferred, and so we can cancel those. I'm going to rewrite our half reactions. So we're going to have 6 electrons plus 3 S2O8 2 minus forms 6 SO4 2 minus. For the other half reaction, we have 4 H2O plus 2 NO forms 2 NO3 minus plus 8 H plus 6 electrons. At this point, if this is a multiple choice exam, you could actually stop here if you're just looking for H pluses. Because they only show up in the one half reaction on the product side. But we'll go through and finish balancing our equation. All right. And so we have 8 H plus on the product side. Question? Yes.
I'm still a little confused where you have the H, like which reaction for H2O.
Okay. So the step where we're adding water.
Yeah.
So you add water when the oxygens aren't balanced. So for these two half reactions, only the nitrogen containing one had a misbalance of oxygen after we accounted for all of the other atoms. And so you add water to the side that needs more oxygen to balance those out. Other questions? You will definitely have to do this on an exam. So practice, yes.
Why was there no water outside that one? Oh, wait, never mind. I see.
Okay. I was worried that you were just going to stop at why. A little bit harder to answer. Other questions? So this is my preferred method of balancing. There are other ways of doing it, but having done some of those other ways, I like this way the best. Again, like I said, you don't have to worry about oxidation numbers. Okay. Go back. Now, sometimes we want to balance redox reactions in base. So much of the balancing in base is the same step as balancing in acid. Okay? In fact, steps 1 through 2 are exactly the same. Steps 1 and 2 are balancing writing half reactions, balancing other atoms, adding water, adding H plus, adding electrons. After you do all of that, before you add up the equations, you add OH minus to both sides of the equation to completely neutralize H plus. Okay? In adding OH minus to both sides of the equation, it's just like mathematically you can add a number to both sides of an equation and it remains equal. So that's what we're doing there. And then what we're going to end up doing is combining, or as we know, H plus plus OH minus react to form water. So we can combine those and we'll end up with water and we can simplify. Back to our list. We completed steps 1 through 2 in balancing for acid. The next thing we do is we look at the number of H plus on both sides of the half reactions. And we're going to add that number of OH minus to both sides. And then from there, so we're going to do one example. So here we have an oxidation reduction reaction where we want to balance in base. This question is going to ask for the lowest whole number coefficient for OH minus. But let's just worry about balancing, let's worry less about answering that exact question. So again, steps are basically the same. We're going to divide into half reactions. We're going to have our iron-containing half reaction, iron hydroxide. I'm going to leave off phases, forms iron, solid. The other half reaction is H2 gas forming water. So, balancing other atoms. For our iron half reaction, we've already done that. There's one iron on the reactant side, one on the product side. Then the other half reaction doesn't have any other atoms. So that's good for now. The next thing to balance is the oxygen by adding water. So in our first half reaction, we have 2 oxygen on the reactant side and none on the product side. So we need to add 2 water to balance that. In our second half reaction, should I do one half reaction and then the other? That makes more sense? Probably. Okay, let's continue working with this first half reaction. So we've added 4 hydrogen to the product side. We have 2 on the reactant side. So we need to add 2 H plus to the reactant side in order to balance those. Everyone see that? And now we can add electrons. So in terms of overall charges, we have +2 on the reactant side of that first half reaction and an overall of 0 on the product side. So we need to add 2 electrons to the reactant side in order to balance those charges. Make sense? Okay, the second half reaction, we're going to stop there with that first half reaction, but the second one, we need to balance our oxygen, and we can add water to the reactant side, 1 water to balance out the 1 oxygen on the product side. Now we have a total of 4 hydrogen on the reactant side and only 2 on the product side. So we need to add 2 H plus in order to balance those. Okay. And then in terms of the charge, overall 0 on reactant side, +2 on the product side. So to balance that, we add 2 electrons to the product side. So combine. So in our first half reaction, the iron-containing half reaction, we have 2 H plus on the reactant side. And so because we want to add, we want to balance in base, we need to get rid of any H plus and replace that with OH minus essentially. And so we can add 2 OH minus to the reactant side and 2 OH minus to the product side. Same thing's going to actually happen just coincidentally with the second half reaction. We have 2 H plus on the product side, so we can add 2 OH minus there and 2 OH minus to the reactant side. So questions on that? People sometimes get kind of weirded out by that step where you're just kind of like randomly adding OH minus, but you're doing a certain number of OH minus consistent with the number of H plus, and that's so we can completely react the H plus and the OH minus, and we want to have leftover OH minus. It is kind of weird, I guess. So I'm going to take this first half reaction, and on the reactant side, we do have that 2 OH minus and the 2 H plus, right? And so if we have H plus plus OH minus, it completely reacts to form water, okay, as we've seen in our acid-base chapters. So I'm going to react those. That's going to give me 2 water. For now, I'm going to leave my electrons, and I'm just rewriting things here. Okay, so now I don't have any H plus left over in that half reaction. On the product side of the second half reaction, again, we're going to have 2 water formed. So we're going to have 2 OH minus plus H2O plus H2 forms, oops, H2O plus 2 H2O plus 2 electrons. All right. At this point, we've done all of the balancing. We need to add everything up. The electrons are going to cancel. That's great. If they hadn't canceled, we'd have to multiply the half reactions by a number. And then we can start canceling water. We have 2 water here. We have 2 water here. In fact, the hydroxide are going to cancel. They cancel. Let's see. This water cancels with 1 up here. Overall, we're going to be left with FeOH2 forms plus H plus. Sorry, plus H2 forms Fe plus H2O. I think that is correct. Questions on that? Yeah, question.
Would it be 2 H2O products? Because the one is only can.
Oh, yep, it is. Yes, there's 1 left over on the first reaction and 1 in the second. Thank you. Other questions? One of the water ended up canceling with another water down in the second half reaction. There's a lot of water in that one. We can come back to that problem next time on Monday if you're